Okay, welcome back to a bunch of lectures on kinetics, chemical kinetics. This video we're going to talk about how to figure out the speed or the rate of a chemical reaction by looking at a graph, or if I give you information in a table. We're going to do it kind of both ways. So here is our chemical reaction. We talked about this in a previous video. So this stuff here is called nitric oxide. Again, I don't really care that you know that. And you can form it by mixing N2 and O2 under the proper conditions, but we want to talk about how fast, or the speed of this chemical reaction. And the way that we're going to do it is we're going to measure the speed of this stuff forming, the speed of nitric oxide forming. There's two ways that you can kind of figure this out. You can either figure it out with information on a graph, or you can figure it out with information on a table. We're going to focus on the table eventually, but let's look at the graph first. So on the x-axis of this graph, there's time. The units are a little bit weird. This is microseconds. So that's a millionth of a second. And the y-axis is the concentration of these different things. So the concentration of N2 and O2 is on this blue line. The concentration of nitric oxide is on the red line over here. And the concentration is also maybe in a little bit weird units. That little thing there is the Greek letter mu, and that means micro, and the capital M means molar. So this is concentration in micromolarity. But doesn't really matter what the units are. It's just concentration on the y-axis, and it's how much time went by on the x-axis. So what they're doing here is they're measuring the concentration of the three different pieces of the reaction at different times. So at the very beginning, at 0 time, well, I've got a lot of N2, right? I've got a lot of N2 and I've got a lot of O2 because I'm over here. And also at the very beginning, the concentration of nitric oxide is 0. There's none of it around. So imagine I have a container. It's filled with N2 and O2. There's no nitric oxide at the very beginning. But as time goes by, the chemical reaction starts to take place, and the amount of NO starts to go up and up and up. And so the amount of this stuff starts to go up, and the amount of the stuff on the left starts to disappear, because the only way you can make NO is to use up some of these other things. So hopefully it makes sense that one of those curves is going up over time. This one's going up because the concentration's going up, and the other curve is going down over time because that stuff is being used to make the NO. The question is, what is the rate of nitric oxide formation between 5 and 10 microseconds? So we want to know, and really this should say the average rate. So what's the average speed of NO formation between these two times? And remember what we did in previous videos. If we want to find the rate, we have to find how much this changes divided by how much time went by. And you can see this also in this table, and it's probably a little bit easier to see because they give you the numbers specifically in this table. Over here in this column is how much time went by. We start at 0 time if you care. And in these other two columns, this is the concentration of N2, concentration of O2 in units of micromolarity, and in this third column, this is the concentration of nitric oxide. And like I said, the nitric oxide starts at the very beginning at 0 time. We don't have any. We have some N2 and some O2. And as time goes by, the concentration of N2 and O2 starts to go down, right? 13.1 is lower than 17, 9.6 is less than 13.1. And so as this stuff goes down, as this stuff is depleted, the concentration of nitric oxide goes up. It starts at 0, then it's 7.8, etc., etc. So all we have to do, it's kind of spelled out here with this red rectangle, is we have to figure out how much the concentration of NO changes between 5 and 10 microseconds, and then divide it by the amount of time that went by, which is the difference between 5 and 10 microseconds. So to do that, we would do 14.8 micromolar minus 7.8 micromolar. That is delta NO concentration. And then we have to divide it by how much time went by, which is delta time. So we have to do the final time. In this case, they care between 5 and 10 microseconds, so our final time is 10 microseconds, minus the initial time that they care about, which is 5, so minus 5 microseconds. So this is going to be our rate once we simplify it. So we can do 14.8 minus 7.8. That is 7 micromolar. And then 10 microseconds minus 5 microseconds is 5 microseconds. So this is, again, this is a simplified version of the rate of NO forming. And if we simplify this, if we do 7 divided by 5, we get 1.4 micromolar per microsecond. Let me just write that one out. So this is our rate of NO formation between 5 and 10 microseconds. In other words, the concentration of NO is going up 1.4 micromolar for every 1 microsecond that passes by. And that's not the speed every point in time between 5 and 10 microseconds. This is the average speed. This is the average rate. Just like our speed in the previous video when we were going down the highway, it wasn't 12 miles per hour the entire time, or it didn't have to be. It could have been a little bit more, it could have been a little bit less, but the average speed was 12 miles per hour. This is the average speed of formation of NO over this period of time. And so that's called an average rate. And basically that's what we just did. We calculated the average rate of a chemical reaction using data in a table. The other thing that I want to point out here is that we calculated our average rate. It was 1.4 micromolar for every 1 microsecond. That's our average rate of formation of NO. It turns out that this rate is equal to the slope or the steepness of the little line that connects the red line between these two red dots, between 5 microseconds and 10 microseconds. In other words, if you could figure out what the slope or the steepness of this line is, it would end up being this number. And so if this line was steeper, if the line was sort of like that, and then you calculated the slope of this line here, this would be a steeper line. That would mean our rate is bigger, because if we have a steeper line, then and the slope of the line is equal to the rate, or the average rate, then since this part here is steeper than this one over here, then the speed of the rate of this reaction would be faster. And if I had a line that was not as steep, like this one over here, then the rate of formation of whatever I'm interested in over here, that is slower than the rate of formation of this stuff over here. So the slope or the steepness of those lines is going to equal the average rate of the chemical reaction. And that is it for this video on how to calculate the reaction rate from a graph or a table.